So we're going to talk more about breadth first search. I'm going to talk about one particular application of breadth first search, which is pretty important. So let me first define something called a bipartite graph. So an undirected graph P equals VE is bipartite So the idea is that V can be partitioned into two subsets. We'll call them L and R for left and right. Such that every edge has one endpoint in each of those sets. So one endpoint in L and one in R. Okay, well, let's draw an example down here. I'm going to make this is my set of left vertices, and this is my set of right vertices. And we can connect them with some edges, maybe like this. Sure, there you go. So, hopefully you can see that. That would be an example of a bipartite graph. In particular, right, there's no edges that go, that connect multiple vertices over here or vertices over here. All the edges kind of go across from one side to the other. So, these show up a lot. Partly we're doing this today because it's an interesting application of breadth first search, but partly bipartite graphs are just really important. They show up a lot. There's a lot of different things you can model using them. So anytime you kind of have two sets of things with some kind of relationship between them, often bipartite graphs show up. We're also going to see that there are a lot of questions you can ask about graphs that are very hard, as far as we know, on graphs in general, but become a lot easier on bipartite graphs. So there's a lot of questions that we can answer efficiently about bipartite graphs, even though for other graphs we might not know how to do it well. So sometimes instead of left and right, we might also talk about like blue and red. You can also think about, instead of thinking about putting the vertices into sets, you could think about giving them colors, like two colors, so that there's no two vertices with the same color that are connected by an edge. And that's the same thing, right? Instead of saying left and right sets, we're just saying two colors. Okay, so I'm going to draw some graphs up here. What I would like you to do is to copy them down, because I'm going to ask you to get in your groups and discuss, figure out which graphs are bipartite and which are not. So, right, when I draw a graph like this, it's really obvious that it's bipartite. But if I had mixed up all the vertices, it may not be as obvious, which vertices you should put in the left group and which you should put in the right group. So, as a very simple example, I don't know, if I drew it like this, right? The way I've drawn this, it doesn't really look very bipartite, but I claim it actually is. I'll let you think about that in your groups. But I've drawn it in an intentionally misleading way. So the point is, can you just find, and then you can think about colors, right? So can I make some vertices red and some blue such that, they're not There's no edge that connects two vertices of the same color. And yes, I can. So like if I make this one red, and, well, I guess, right, I just turn it in this case. But I can make these two red and these two blue, and that works. Okay, so I'm going to draw some graphs up here. Copy them down, because once you get in your groups, you won't be able to see the board anymore, right? That'll be over in this other meeting. So, all right. I'll give them letters so we can talk about them later. So this is graph A. Here's graph B. Here's graph C. Let's see. Okay, this is graph B, and then make one over here. So this is that's a vertex there, by the way. Make that clear. That's just E. I'm going to do one more. Okay, something like that. I'll make this graph F. So as soon as you have copied those down, you can go jump in your groups, and we'll just take a few minutes and see if you can agree in your groups which of these graphs are bipartite and which are not. And then when we come back, we'll talk about why. All right, welcome back all. So let's talk about these, right? And number one, we want to figure out, what are the answers for these. But number two, with an eye towards, some kind of general method. Can we come up with a general way of telling? If I just show you an arbitrary graph, can you figure out if it's bipartite or not? Group A, how about graph A? Do you think it's bipartite or not?
We said no.
Okay. Do you have a way to argue why it is not?
If you put you split it 1 and 2 of any combination, the two that are together will always have an edge between them.
Right. Yeah. So if I try, like if I put, yeah, you're saying right. There have to be two in the same set, left or right, or two of the same color, we can say, and they're always going to be next to each other, right? So if I can make, this blue, and then this red, maybe, but then like I'm stuck. Well, no matter what color I give this, it's going to have the same color as either this one or this one. Okay, so this is not bipartite. Group L, and how about graph B?
It is bipartite.
Okay, can you prove it?
and then the upper left and the bottom right in the group.
Yep. That works. Right, to show that a graph is bipartite, all you have to do is, I don't know if y'all can see those colors at all, but can y'all see that, sort of, Effie? Alright, well, right, these, here, probably this one. Can you see, how about, can you see that better? Is that a better color? Yeah. The lighting is not great in here, so make those green, and then seem to be out of yellow chalk. All right, never mind. Whatever. These two are in the same group. These two are in the same group. To prove that a graph is bipartite, all you have to do is say exactly how to put the vertices in groups, and just show that there's no edges between two with the same group. Okay. How about group G? What did you think about graph C?
We said.
Go ahead.
We said yeah. Oh man. I'll let you handle it. Okay, we said no. The way we were doing it is we would pick one vertex, and then each adjacent one we would give it to a different group, and then we would just keep like alternating like that. And if you do that, then eventually you have two of the same group sharing the same edge.
Mm-hmm. Yeah. Yeah, so someone suggests like slashing through this. Yeah, so you're saying kind of if I understand what you're saying, if you kind of get started, you're like, well, let's try like making this one color and this one another color. But then, you know, it's kind of forced, right? Like I have to make this one a different color than this one, so I have to make it this color. But then I have to make this one a different color than that. I have to make this one a different color than this. Well, but this one now I'm stuck, right? It's the same problem we had over here. Like there's no color I can make it that would work, right? So that's not. This is okay. All right, group O. What do you think about graph D?
So for group O, we didn't explicitly say it, but kind of going with the theme of it, you can kind of start at the leftmost vertice and label that whichever color you want, or no, the one higher, the one above. Okay. And then for each possible edge, you label every next vertice a different color. So you just do for every edge versus doing one at a time.
Okay.
And then you continue that process, and you'll find that all of them, there are no of the same colors. So if you start with the blue one at the top, you'll get two greens, and those work out with the blue that you already have. And then you can then start from another one. So the furthest right one, you can label that one blue.
And this one too, I guess.
The kind of and that one you should do blue, and that works out. And then the middle one will be green.
Yeah. Good. Yeah, I think that works. And what about graph E? What do y'all think? Bipartite or not? Just anyone. Yeah, I see a thumbs up. Should we vote? I don't know how to do voting things. So I hear several yeses. So I agree. I think it is bipartite. And we could do a similar thing as this, right? How about graph F? Thumbs down? Yeah.
No.
Yeah, graph F actually, I mean, is kind of similar to graph C in the way that matters, right? So, okay, did anyone, I don't know if you talked about this in your group, right? I didn't ask you to explicitly, but anyone want to make a guess or a conjecture as to some kind of general property that you could use to distinguish bipartite from not bipartite graphs? Or any thoughts in that direction?
Yeah, if there's like a, I guess I'd call it like a cycle with an uneven number of vertices, then it can't be bipartite.
Okay, yeah, so I agree. Right, so we saw that like here, right, anytime you have a cycle that's got an odd number of vertices, if you're kind of forced to assign the colors going around, but then it's not gonna match up at the end. You're gonna be stuck having to assign this like two different colors to the same vertex. Okay. What do y'all think? Do you think? Do you think that's an if and only if? So in other words, if a graph, wait, how do I say this? So I think what Cade just said is, if it has an odd length cycle, then it's not going to be bipartite. Is that right, Cade?
Yes, that's what I said.
Okay. So how about the opposite? Like, if it doesn't have any odd length cycles, is it definitely bipartite? What do y'all think? Or could there be a graph that has all even length cycles, but it's still something goes wrong and it's not bipartite?
Hexagon with a point in the middle pointing to everyone for good.
Okay, let's try it. So you want a hexagon and then a point in the middle.
Isn't it a bunch of odd numbered cycles though?
Say that again?
I said if you do that, isn't it just? I mean, it is a hexagon, but it's made up of a bunch of uneven or a bunch of odd numbered cycles. So.
Yeah, that's true, right? All these triangles, like this is a like 3 cycle here. Yeah, so I agree this is not bipartite, but it does have some odd length cycles. So other thoughts? Either of a graph that either ideas for a graph that has all even length cycles but is not bipartite, or an intuition or argument why like that's not possible. Maybe we should just take a vote. So use your little like hand raisey thing in Teams. So if you think, let's see, what should I say? Raise your hand if you think it's possible to have a graph with all even cycles that is nonetheless not bipartite. Okay, and now raise your hand if you think any graph with no odd cycles is definitely going to be bipartite. Okay, so a bunch of people raising their hand. Good. Cool. So you all have the right intuition. It turns out this is true. So this is an if and only if statement. So the thing Cade said, a graph is bipartite if and only if it has no odd cycles. So let's prove it. So theorem. An undirected graph G is bipartite if and only if. Have y'all seen this before? The abbreviation IFF to mean if and only if? Probably you have, but if and only if it has no odd cycles. Right, and by odd cycle I just mean a cycle having an odd length, like an odd number of edges. Okay. So one direction, so this is an if and only if, so we need to prove two different directions, right? One direction is pretty easy. So this direction says if a graph is bipartite, then it has no odd cycles. So I claim this one is not very hard to see. Right? The reason is if it's bipartite, then any cycle, right, any path at all, has to bounce back and forth between the left and right sets, right? Because all the edges go from left to right or right to left. So as I follow a path, I'm going left, right, left, right, left, right. And in order to come back to where I started, I've got to go through an even number of, left, rights to get back to the vertex I started at. I could go left, right, left, or I could go, left, right, left, right, left. So any path in a bipartite graph must alternate between left and right, hence any cycle must have an even length. Right, and actually, when y'all were thinking about this, I think you were, like, the thing that Cade said was actually equivalent to this. It was like the contrapositive of this. So what Cade said is, if there is a cycle with an odd length, then it's not bipartite. Right, so the contrapositive is you flip around the if-then and you negate both the sides, and it's equivalent. But we could think about it this way too. So the other direction is more interesting. So in the other direction, we have to show that if I have a graph with no odd cycles, then it's bipartite. This is interesting. It seems less obvious how we would go about doing that, right? Because to show something is bipartite, we have to show, how do you split up the vertices into left and right sets and show there's no edges between them. But all we have to go on is that there's no odd cycles. It seems harder because in the forward direction, it's like we're told something positive about the graph. We're said it definitely is bipartite, which tells us a lot. It says, okay, there's these left and right sets and all the edges, blah, blah, blah. And then we have to say something that there's not. And it's like, well, if we know something that is true about the graph, it's kind of easy to go from that and say, well, then there's not this thing. But if all we're told is you have some graph and it doesn't have odd cycles, how do we go about finding the right way to split up the vertices? But we can do it. And we are going to use I'll say a proof by algorithm. What I mean by that is, right, to prove that a graph is bipartite, I have to show what are the left and right sets that I'm going to split the vertices into, and how do I know that there's no edges, all the edges all go between them. And one way I can do that is by saying, well, here's an algorithm. If you run this algorithm, it'll tell you what the left and right sets are going to be, and here's why they'll be correct. So, how's this going to work? And I think, actually, you know what? Yeah. Instead of me just telling you, let's take 3 minutes. So we'll come back at 9:50. 3 minutes in your groups. Just talk about this for a little bit and say, how would you, if I gave you a graph, could be some really complicated graph, but I promise there's no odd cycles. How would you decide how to split up the vertices into left and right sets so that all the edges go between left and right? Okay, go talk about that for 3 minutes.
So Kate and I were talking about doing some sort of breadth first search on the first, like just on any random vertex pretty much, and then you keep track of what its parent was, and then like each loop you went through, you give it the opposite of the parent.
Okay. Yeah, I like that. And that's I think, like when I think it was David was telling us how to color this graph, that's kind of what he was doing. David, when you were talking about this, were you thinking of it explicitly as a breadth first search, or were you just, it doesn't really matter, but I mean, like, that's what we were doing, right? We're like visiting all the vertices next to this one and giving them the opposite color, and so on. Okay, so good. So that's exactly the right idea. So let's write it up. So yeah, we're gonna pick an arbitrary starting vertex. It's kind of funny that it doesn't really matter where you start. You can start anywhere and it's going to work. Now depending where you start, you might get different colors, but it doesn't really matter. I mean, you're going to get something that works. So, and run a breadth first search. And this is going to, so I'm going to say it this way, which amounts to the same thing that Mitchell said. So generating layers L0, L1, L2. Remember when we talked about breadth first search, we said there are these layers, like L0 is the vertex S, then L1 is everything one step away from that, L2 is everything one step away from L1, and so on. So you know, it's like how far away you are from the start vertex. And then we're going to define L, like I need to define sets L and R. I guess it's a little confusing that I'm using, this L stands for layer and this L stands for left. But anyway, L0 union L2 union L4 union ... and R is going to be, you know, all the odd ones. L1 union L3 union L5 union ... Right, which amounts to the same thing that Mitchell said, okay, we keep track of the parent, and if we're, you know, everything in layer 1 has something in layer 0 that's parent, so we give it the opposite color. And then layer 2, you know, we're back to this first color again, and then so on. We keep flipping back and forth. So the question is why this will work. Why this is guaranteed to work. So remember, there's a property of breadth first search that says any edge in the graph, like it could be within the same layer, could be between vertices in the same layer, or it could be between vertices in, you know, layers that are one apart, but you'll never get things two or more apart. So there can't possibly be an edge like that goes from a vertex in L0 to a vertex in L2, for example. Right? So the only thing we have to worry about is an edge that goes, like say from a vertex in L2 to a different vertex in L2. Right? That would be not allowed, because then we would have an edge that, you know, both endpoints are in this L set instead of going from L to R. So let me write that down. So by properties of breadth first search, no edge can go between layers more than one apart. Okay, so all we have to show, and we just have to show right, there can't be any edges. So there can't be any edge between two vertices in the same layer. Right, because I want to show that this is a valid partition of the vertices that makes the graph bipartite. And I need to use the fact that we're told this graph has no odd cycles. Okay. Mitchell, you said you can't read the top line of writing, like up here?
Yeah.
That's weird.
It's just, it could be my internet, I don't know. It's
Yeah.
blurry for me.
Oh, I see. So I said by properties of breadth first search, no edge can go between layers more than one apart. Yeah, it is a little blurry, isn't it? Yeah, sure. So let's say suppose there was so suppose there's an edge xy such that x and y are in the same layer. And then I'm going to look at the breadth first search tree. So here I've got x and y. So I'll say look at the breadth first search tree. Here's x and y, they're in the same layer. And then, there's like, I'm drawing this squiggly because it's not necessarily a single edge. It's like a path of a bunch of edges, but, this is a tree. So eventually they've got like a common parent in the tree, right? When I did my breadth first search, I went down layers and I eventually got to x and I eventually got to y, but, I started from a single vertex, so there must be some common parent they have. We'll call it z. And this is an edge, right? So let's say this has height h, right? So that is the height, the number of layers from z down to the layer of x and y is h, right? So this is a cycle because I have a path from z to x and then an edge from x to y and a path from y to z, right? How long is this cycle?
Two H plus 1.
2h plus 1, right? Because these two paths are the same length because they're going from this layer down to this layer, right? And the layers of breadth first search tell you exactly how long the paths are. And then this is just one. So z is the common ancestor, or a common ancestor of x and y. The length of this cycle is 2h plus 1, right? But that's an odd number. And we were told the graph has no odd cycles, so this is a contradiction. So that cannot actually happen because the graph has no odd cycles, so there can never be an edge like this between two vertices in the same layer, because that would create an odd cycle. Okay, that's it. So the cool thing is, right, not only did we prove this theorem, right, but because we proved it by giving an algorithm, like it actually gives us a way to like efficiently test whether a graph is bipartite. So if I just give you a random graph, you can just start running a breadth first search, and every time you look at an edge, you look at the level map, or the layer map, whatever it's called, to see if the two things on the ends of the edge are at the same level. And if you ever find an edge where they're at the same level, you just say, nope, it's not bipartite, I just found an odd cycle. And if you never see such a thing, then you say, yes, it is bipartite, and in fact, here are the sets. Like I just say, here's the alternating levels, and that gives you, what the left and right sets of the bipartite graph are. So it turns out, even given an arbitrary, complicated drawing of a graph, doesn't matter. You can run this algorithm and like separate the vertices out nicely into sets if it is bipartite, or find an odd cycle if it's not. That's like that's sort of the ultimate, right? As opposed to just having a theorem that says, well, if this thing exists, then this other thing exists. It's like, nope, here's an actual procedure you can use to know for sure which it is. and not only to know, but to like be able to prove it to someone else.